This week's multiple choice Monday is about lattice enthalpy, defined as lattice enthalpy of association. So if you've forgotten what lattice enthalpy is, we should remember it's the formation of 1 mole of an ionic lattice, an ionic compound, from its ions in their gaseous state. So for example, if I were to do an equation for the lattice enthalpy of magnesium oxide, it would be taking the Mg2 plus ion, the O2 minus ion in gas states, and making 1 mole of solid magnesium oxide. So that's quite an unusual situation. It's not like a standard enthalpy change that we could measure in a lab. It's something that we would work out indirectly using a Born-Haber cycle. And it's really measuring the strength of the ionic bond. So you can think about lattice enthalpy as being equivalent to covalent bond, mean bond enthalpy, the sort of values where we compare the strength of bonding. That's what we're doing here. We're simply comparing the strength of those electrostatic attractions between oppositely charged ions. And all of those electrostatic attractions depend on the charge on the ions and the size of the ions, and you may have been taught to sort of group those together as one thing, charge density. So how much charge there is, whether it's a +1, a +2, -1, a -2, etc. And then the radius of the ion, so how much that is spread about, which is just related to its position in the periodic table. So which period it's in, how many shells of electrons we've got, and therefore the size of the ion, how much that is charge is spread out. Because the closer the ions can get together, the stronger the attraction, and the higher the charge, the stronger the attraction as well. And so in fact, our answer was MgO. But how can we work that out? Just by using the periodic table. And also let's get an idea of how different these lattice enthalpies are. So if I look it up, magnesium oxide has a lattice enthalpy. These are all negative values because that's what we mean by saying they are exothermic. We're making bonds, so energy is given out. So for magnesium oxide, it's 3791. Let's compare that with magnesium fluoride, which is -2957. Let's have a look for calcium chloride, -2258. And then our sodium oxide, which is -2478. So you can see that the magnesium oxide is by far the most exothermic out of all of them. And the reason for that is because charge is the most important, and in fact these ions are both very small and high charged, and that is because we have a +2 and a -2. In B we have +2 and -1. Now we do have 2 lots of -1 ions, and fluoride ions are very small, which is why B is the second most exothermic lattice enthalpy. Then in C we've got calcium chloride, and you can see what a difference it makes. So we have the same charges as we have for magnesium fluoride, but calcium is below magnesium in group 2, and chloride is below fluorine in group 7. So although we've still got the same charges, +2, -1, we're now in period 4 and 3, whereas in here for magnesium we're in period 3, and for fluorine we're in period 2. Then if we look at sodium oxide, it's a little bit higher than the calcium chloride, and that's because we've got +1 but we've got -2, and the oxide ion has got a very high charge density indeed, and so therefore we've got slightly stronger. So what we wouldn't be expected to do, for example, in a question we wouldn't be expected to compare C and D, because there's too many variables going on. So we've changed the charge on the cation and the charge on the anion, and we've changed the period that those are in. We wouldn't have to make that comparison, so we'd never be able to say which one out of C and D has the higher or more exothermic lattice enthalpy. We can see that it is sodium oxide, but you would not be expected to predict that. So what you're going to go for is highest charge as a priority. If they are the same charges, then you're going to look at the period. The higher up the periodic table, the smaller that ion, and therefore the stronger attractions. You might have done stuff about theoretical versus experimental lattice enthalpy, and you may have thought about like different sizes on cations and anions and degree of covalent character. Now, none of that is important when you are simply looking at which is the most exothermic. You want to focus just on size of ions, charge on ions, charge being the most important factor. So, if you want to know more, don't forget to look at my revision materials, ckchemistry.co.uk. While you're there, you'll get a pop-up and you can sign up for my free chemistry revision club if you're not already on it. My online A-level masterclasses. So I've got a few spaces left for the live classes. If you want to join those live, they're starting this week on Wednesday. There's going to be 2 a week now until the final exams, pretty much. So there are still 15 lessons left. If you can't attend live or you don't want to, there is a 50% discount until the end of May on the recordings, which means that you can access 23 lessons plus predicted papers for, I think, about £32.50. So really, really good value, but that's only available, that 50% discount, until the end of May. And you can find those on my website as well. And of course, if you subscribe to my YouTube channel, you're going to be informed of new videos every week.